You're listening to 106.9 Shin FM here on the home of UNE's student-powered radio, and I'm joined today by the wonderful Professor Chris Kirkland, all the way from WA, from Curtin University, and we're going to be talking about a really fantastic study that could change how we look at our planet's crust formation, thanks to the chemical, I guess, geological archive of zircon crystals, which I'm sure everyone here is fairly familiar with. They're very fascinating. So, thank you so much for joining me today, Chris. I hope I've sort of given at least a good enough understanding of what we're talking about that we can dive into it.
Sounds lovely. I'm pleased to talk to you, Ash. Yeah, I think you're right. Zircons are this fantastic deep time archive of our planet. But one of the neat things with having such a deep time archive is we can actually compare things on a much larger scale. So, I mean, comparing things right throughout Earth history, but also then maybe look at some of the information that comes from astrophysics. So, try to connect information from astrophysics and geology. And that I think is quite exciting about some of the things it might tell us.
And so that's very much what this paper that you've recently published and has been accepted into physical review research is really focusing on. But before we dive into that, I guess I just want to talk a little bit about you and your background. How did you come to be involved in this sort of study, and what is your interest in the connection between geology and astronomy?
Yeah, so yeah, I've been working as a geochronologist, so basically figuring out the age of rocks and minerals for quite a long time. I started out actually working with the Geological Survey in Western Australia, so collecting, very large data sets of the age of minerals. And when you start to create, really large data sets, you start to see patterns within those data sets, and those patterns potentially can give us extra information about geological processes. And really, it's from that you start to think about other sources of information that might have patterns within them, because that lets us maybe make models that better understand our planet, but also our universe. So it's really going from the small, really small scale, like individual mineral grains, shooting laser or ion beams into those mineral grains to calculate ages, but creating vast data sets of thousands and thousands and millions of analyses, and then looking at the patterns within that, and then think about what those patterns might mean, and then extrapolating that out to the biggest scale. So the biggest scale would be, cratons on our entire planet, but then we can go further, to our solar system. And hey, you can even go bigger again, and let's think about our galaxy and some of the patterns within that. So that's the scale range that I find really fascinating.
Yeah, I mean, it's not something that I think a lot of people make that connection to. So how did you go from I'm going to shoot lasers at rocks to really simplify it down to then looking at how those that data, that massive data set, relates to maps of gas in the Milky Way? Because that's the comparison, right? Is looking at chemical changes in the zircons to gas maps of the Milky Way. How did you make that leap?
Yeah, so I mean that's one of the hard things, right? So in geology, we're looking at typically processes within our planet. There's also planetary geology when we're looking at processes on the moon and Mars. But those patterns that we see in terms of events through time, we can use the fact that there is periodicity, so events happening on a specific frequency. We can understand that on Earth, but we can also understand the frequency of events caused by our position within our galaxy. So, to go into a little bit more detail, our solar system migrates around the Milky Way. So, the Milky Way is conventionally considered to have four arms, and those arms are arms of gas and dust. The arms move as well. So, these density waves of gas and dust are moving, but our stars are also moving. And what's interesting is the rate of movement around the central black hole, so everything is spiraling around and around, is not the same. So the at the distance we are out from the central black hole, our solar system is actually moving a little bit faster than these density waves. So because we're thinking about things through vast amounts of time, what that actually means is that our solar system and Earth will have migrated through regions of higher density gas and dust at certain periods of time. And these are only small changes, but small changes in the relationships of it's basically known as the gravitational tide or galactic tide. Small changes in the amount of density, more stars within the local neighborhood can cause knock-on effects, and it's those knock-on effects that we might be able to see in the geology record of our planet, which is quite fascinating, right? So what we're talking about is a connection between our planet and ultimately a connection with where we are in the in the Milky Way. So it's basically using time to go between geology and astrophysics, which is kind of cool, I think.
Yeah, I mean, it sounds pretty spectacular to me. It feels like I read a lot of articles and releases on similar topics like this for my job, but this is sort of really the first one that I've actually seen that said, "Hey, here's a direct connection between these two processes," and I think it's really, really fascinating, particularly in how it's going to change. And I think it's something that you said, change our understanding of how geology and astronomy really connects when it comes to studying that and opening up new avenues for research. And, I just think it's something that is always going to be fascinating. It's not something people talk about a lot. And yeah, I mean, hang on, I'm rambling for a second here. It's
So it's all right.
I get stuck in those little loops of like, this is really, really cool. How do I get into my next question? Um,
So
but
we can
one of
talk
the
about.
things is that in the meteorites
Mm,
is
yeah,
sort of what I wanted to look at
yeah,
is
yeah.
that meteorite impacts and helping to create our planet's crust, because that's kind of
That's a
the big thing.
connection.
Is that's the
Yeah,
connection. It's
that's
this
the
is
connect.
how it's changed.
Yeah, so that's the connection, right? So we've been talking about the kind of data sets, if you like, that make the link between geology and astrophysics. So we've got a record from geology about the time that crust forms, but also an indication of where that crust forms from geology. So we can go into that in a little bit more detail. But basically, we've got a record about the geology of our planet. That's a deep time record. We've then got an astrophysical record that tells us roughly where we are within the position around the Milky Way. And we link those two things with time. Um, so then the interesting thing is there seems to be a connection between we're getting more diverse signals in geology, more diverse magmas, and when we're in a spiral arm region. So then the question is, what is the connection, right? What is the connection between where we are in the Milky Way and the production of crust on our planet? And the most obvious kind of suggestion then would be that the flux of impactors, the flux of meteorites and comets coming into the inner rocky planets, so not just Earth, but also probably the Moon and Mars, would have varied because of where we are in the galaxy, and that conceptually kind of makes sense. But it's this model really explains this potential connection between geology and astrophysics. So what we're talking about really is the flux of impactors. So it's not going to be one or two; it's the probability of a higher proportion of stuff coming in at periods of time when we're within the spiral arm regions.
Yeah, and so for people like me who aren't sure what flux means, is that that like an influx of meteorites, or is it sort of a byproduct of them hitting the crust?
It just means that any over any given period of time, there would be more impactors during periods of time we're within a spiral arm region. So you can imagine outside a spiral arm region, you're maybe getting, let's say 10 impactors per um, million year. We go into a spiral arm region and you're at 20 or 30. Now, those rates might not be right, but what we can see is there seems to be some connection with a change in how the planet's crust is responding during these same periods of time. There is obviously challenges, right? We're making models here to explain the patterns in the data that we see, and correlation isn't necessarily causation. But I think with having data that is strongly correlated, it allows you to make interpretations about possible explanations for the data we see.
Yeah, I mean, that's exactly right. Correlation doesn't equal causation, but if there's a correlation, it probably does mean there is some form of relation there. It's just about, looking at what it is to understand it. And meteorites do such fascinating things when they impact with planets. There's these ideas that they've brought water, other chemicals necessary for life to Earth and to potentially other planets. So I think looking at things like how it impacts planetary formation is really fascinating because it's going to change how we look at other planets as well, in our galaxy or beyond, even at a certain point.
Yeah, that's right. So what we uh, think possibly happens is with this increased number of impactors, including some dislodged from the Oort cloud, and we can talk about that in a minute, but these are coming in with really high velocity. Um, and they're excavating large volumes of our planet's surface. So when you excavate a large volume of our planet's surface, you cause what's called decompression melting. It's basically like taking the cork off a champagne bottle. The mantle will rise, so the deep molten rocks will rise, and that might take a period of time. But also, you will start to create other kind of circulation cells, so take other crust and drip it down at the same time. So it provides a mechanism for resurfacing and recycling the surface of our planet. So before plate tectonics started, so before the crust was well regimented into these large plates that move apart and move back together again, impacts might have been very important for producing similar sorts of processes, creating new crust through impacting, but also causing the recycling of crust. And that's kind of what we see in the record within our zircon crystals. So our zircon crystals give us an age because they contain uranium, and uranium changes to lead over time. So that's a clock. But not only that, we can look at other isotopic signatures within the zircon that tell us about the magma that crystal grew in. And if we look at enough data, what we see is that during the spiral arm region times, the oxygen isotope signature or the signature of the magmas become much more diverse. So we're seeing magmas being formed in a much wider variety of places. So deep within the planet, but also shallow. And that kind of fits with what you would expect during periods with more impacts. You've got a more chaotic system during those periods of time.
Yeah, it kind of this metaphor might be way off, but it almost reminds me of tilling the earth in a
Yeah,
way,
yeah.
but on a much, much larger scale. Instead of just doing the soil, it's everything else as well, like shaking it all up and re-putting
Yeah.
it in.
So
Um,
so that's lovely. There's actually this term called impact gardening. Um,
Nice.
yeah, no, it's a scientific term. So yeah, it means exactly what you're talking about. Um, there's also another interesting thing, right? So with impact gardening, what you do is you remove the record of craters. So by impact gardening, you're actually removing that record of craters. So which is why, counting the number of craters at specific points in time might be another mechanism to test this. But the problem with that is our kind of cratering record, right, is kind of self-erasing. It's like rubbing
Mm.
itself out. So that's why these zircon crystals, because they survive, they're so robust and so hardy, they give us this really deep time record of processes. And that's why they're very special and why, they're the geologist's best friend.
Yeah, I hear about zircon crystals all the time, really. Like, and they're just used for so many various things. And I'm really glad that you went into it a little bit because one of my next questions was about what makes them so special and why they have sort of this geological memory. So it's the uranium and the isotopes within it. Is that what makes them unique compared to other minerals?
So there's multiple things. One is they're quite ubiquitous, so they occur in many different rock types, but their chemistry is really special and helpful because they're timekeepers. So they give us an age. And that's because, like you said, of the uranium to lead conversion. So when they initially grow, they don't like to have any lead, which is actually really handy for us. So that means if we measure them today and we find lead, that lead has come from the decay of uranium. So if we know the amount of uranium and lead today, and we know that conversion rate, which we do, then that gives us a clock. So that's the first thing, right? So we've now got a mechanism of telling the age of this crystal. That's really useful by itself. But we can also go to that crystal and analyze a whole range of other different things in terms of its chemistry, but also its other isotopes. And that lets us piece together more information. So like I said, we can look at the oxygen isotopes. The oxygen isotopes give us a bit of a proxy, a bit of an indication where that magma came from. So where the crystal grew, did it grow deep in the earth? If it grows deep in the earth, it's got a magmatic signature that is more like the mantle, or did it grow in the shallower crust? And if it grows in the shallower crust, it's probably interacted with surface water, and that changes the oxygen isotope signal because we know our planet was wet, had oceans from very early on. And that's actually the reason we know it was wet early on, because if we look at old crystals and their oxygen isotope signal, it tells us that there must have been water on the planet from very early on. So you actually touched on that when you said, oh, meteorites might have delivered water. Yeah, that's one idea, but it's also possible that there was a lot of water already in our planet when it first formed. So you can get so much information out of these crystals. I mean, that's only at the tip of the iceberg of what you can do with them.
What a I'm always happy to dive down into the rabbit hole, so to speak. What are some of the other things that you can do
Yeah.
with zircons?
Okay. So there's another isotope called hafnium, which is really interesting as well. So hafnium basically tells us when material came out of the mantle. So um, my surname is Kirkland. You can tell I'm from Ireland and Scotland, right? With that surname, we essentially can do the same with our zircon crystal. We essentially can get a surname out of our zircon crystal that tells us when it came out of the mantle. So it's like me um, getting my age taken, but not only that, it's I can get the age of my parents as well. It's kind of crazy, right? So we can look at we can look at the first stage of the crystal growing, but we can look back even earlier into that crystal's history, and it's trapped within the isotopes. So there's all these different layers of information we can get because it's been such a powerful mineral, right? There's huge databases now of this mineral, so its age and its chemistry through time. And it's those large databases that give us the ability to look at patterns, right? If we didn't have a huge database, we would not be able to see these patterns. So it's only with these vast amounts of data that we see these patterns that then we can compare to stuff on a completely different scale, right up at the other end, at the astrophysics scale, looking at um, you know atomic hydrogen, which is measured using radio waves. Um, but we can link the two with time, so we get time series, and because they're got time series, we can essentially overlay them and compare them. If we didn't have that time aspect, we wouldn't be able to compare these data sets. So it's using time to link vastly different sources of information, and I think that's one of the special things maybe about what we're able to do. As geologists, I think we frequently think about things, just related to our planet, and that's natural. There's this concept you might have heard of called uniformitarianism. So it's basically what we see today, we can use to extrapolate into processes in the past, and that's fine. But when we start to think about the early Earth was a vastly different place to present day, and the frequency that events happen might have been quite different. So it then becomes, I would argue, a system that's less uniform, and we need to start thinking about other processes. And I think, astrophysicists have been thinking about this for a very long time. So I think taking some of the ideas out of astrophysics and merging them to geology is a really important frontier in understanding our planet and why we're here.
And I think it's something that can be translated, across both. Because one thing that I've noticed in geology and in astronomy and astrophysics is just the sheer amount of the scale of time that geologists and as astrophysicists look at is they're not thinking in thousands of years or hundreds of years like historians might be. They're thinking in millions or billions of years. This really massive scale that honestly hurts my brain to think about a little
Yeah.
bit. But
Yeah.
you both have this incredible font of knowledge and data that's gathered that shows this massive timeline on this unprecedented scale. And
That's
I
right.
just think it's a really good way to look at things, and I'm really interested to see how more studies like this, intertwining the two, are going to shed more light on it.
Sure. There's this also wild aspect as well that I think is quite fun to think about, right? Which is in astrophysics, right? Where we're currently sitting in our solar system, we're within the Milky Way, so it's actually quite difficult to map out the Milky Way because we're right within it. It's not like we can send a satellite out far enough to take an image back. So all the beautiful pictures, right, you see of the Milky Way are actually, they're artist renderings. We can't go away far enough and take an image. What we can do is we can use radio waves to see through the gas and dust and create a kind of a map and use mathematics to kind of flatten it out into the spiral arms. But a really interesting thing is, right, that looking through the Milky Way, right, if we're looking through the Milky Way, we're going to reach a point that we hit the black hole in the center of our galaxy, and we can't really see through that black hole. Okay. So there's no kind of light's not going to be able to pass through it, and radio waves and stuff won't pass through that structure. So, how do we understand what's on the far side of our Milky Way? Um, uh, there's That's potentially where geology can help, right? Because at
Yeah.
some point in our history, we'll have actually been located on the far side of the black hole, right? So that's one area where I think you're right that the two subject areas can help each other. So it roughly takes 200 million years to go between the spiral arms, and our planet, I think, will have orbited about 6 times around the entire galaxy. Um, so there is information entrained in our geological record about the far side of the Milky Way. Learning how to read it is obviously hard, and we have to decrypt that information that we see within our geological records from internal processes to our planet, which might be more dominant. But there could be a record of other processes, and those other processes could be impacting. And if impacting says something about the galactic environment, then that provides information about that region that we can't actually see with using astrophysical techniques. So there could be mechanisms of extracting some information from that, the far side of the galaxy, which I think is kind of an exciting thought. It's very
Yeah.
conceptual. It's very conceptual, but if you get your head around it, kind of like, whoa, that's really cool.
Well, no, it is because it's, as I was saying, that this is on a massive timescale, but we have archives of it buried in the earth, and I think you're in a great place to look at it because, to my knowledge, Western Australia has a really high level and some very special zircon crystals that are very different to other locations. And if we're going to be focusing on using them to understand the galaxy and the different processes and formations and even, potential different gas makeups of the different spiral arms, there's a lot that can be there. So,
Yeah,
maybe someone listening out there's going, I know what I'm going to do for my masters now.
yeah. So it's really about the connection, So the connection between you know the the galaxy, if you like, and astrophysics, and the density of spiral arms and processes on Earth. The reflection might be an impacting, so the impact flux, so there might be more impacts. So we might not get, direct information about gas and stuff, but we can use it to infer about densities of spiral arms and where the arms actually sit. So the arms are probably not rigid entities. They're probably slightly bent and diffuse in places and more rigid in others. So actually using geology to map out these kind of structures is potentially possible. You're right about WA as well. WA is fantastic because it's got really old bits of crust, and really old bits of crust allow us to create these really deep timelines, which is what we need to look at. And a lovely example of that is you kind of mentioned these special rocks, which one of them is Jack Hills, which is a sedimentary rock. It's called a conglomerate, which means it's got blocks of other sedimentary rock within it, but it contains exceptionally old zircon, the oldest on the planet. Um, so looking at Jack Hill zircon has been very important for our understanding of Earth, because that's exactly where oxygen isotope analysis have told us that we live on a planet that had water from very early on. It's those crystals that actually say that. Oxygen isotope analysis of those grains is where that information came from. Um, and the techniques we use to analyze these grains, which are laser beams and ion beams, are the same techniques we use to tell the age of ore deposits. And there's this nice interaction between blue sky science, doing this kind of really big picture geology, and also the same techniques and exactly the same tools and telling the age of things, and the chemistry is exactly what helps reduce exploration risk and helps us find our next ore deposit, which is pretty important for society as well, right? If we want stuff for our smartphones and our
Yeah.
TVs, we're gonna need to find more resources, and we use the
Yeah.
same techniques.
Is there a danger of running out of zircons through, like, I mean,
No,
that's sort of a dumb question, but I
no,
guess,
it's
like,
not.
I'm
It's a
thinking
good
about, like,
question.
mining and
Yeah.
processes that could
Yeah, it's
potentially,
no,
blow
it's a
things
really
up.
lovely, it's a really good question. So yeah, in terms of the amount of grains that are analyzed, it's a lot, but you know, pretty much everything. Like you walk across a beach, um, there's going to be bazillions of zircon grains in that. In fact, zircon itself is actually an interesting mineral as a feedstock for it's used it's used for quite a number of different processes. Some of it's used for like a casting medium because it's got a really high melting point. So you can use zircon sand to kind of create the shape of, let's say, a turbine blade or a joint for a limb. You know, if you're going to have a replacement limb, so it's actually using quite a lot of technology things. But you can imagine how many millions and
How
millions and
much would
millions of
go into
zircon
it?
grain
Yeah, yeah.
you need as a feedstock for like doing that kind of stuff. So what we're doing is only a really small proportion, really small proportion.
Yeah, yeah.
But what is interesting is like, we actually go through quite a lot of reference material. So reference material are zircon grains. We know they're aged really well of. We fire laser beams and ion beams into those to calibrate our instruments. And because we're doing so many of these analyses, there's always a need to have well characterized zircon that we can use as standards and references. And the community has those and shares them, which is great. But yeah, we burn through quite a lot of that material.
Yeah.
But that's just
So
another part of the job.
yeah, makes sense. I guess because I was thinking of them as, like, being, like, small. Because being in Armidale, obviously, there's a big fossicking area. There's actually, like, a zircon fossicking place down here. So I was picturing, like, small and able to pick up. Obviously, not anything massive, but visible to the eye and things like that. But you're saying these are also the size of grains of sand, so absolutely tiny and able to just
Yeah, that's
have a giant handful.
that's the majority of them. The majority of grains that we work with are probably on the order of about 100 to 200 microns long. So that means in the width of a hair, you'd be able to get several grains. And then into that, we fire beams that are about 20 microns across. So again, you get multiple beams with multiple analytical spots within a single grain. Um, and how we actually do this, we do use a pair of tweezers and pick individual grains. So that means, no coffee for about a week beforehand when you're picking individual grains with tweezers. You can just about see them with the naked eye. It's generally done under a normal binocular microscope. But yeah, I'm always amazed, like with a pair of tweezers under a binocular microscope, you can actually move things about quite efficiently, down to about 10 to 20 to 30 microns. You're still able to just about pick stuff. Most grains are about 200 microns, 300 microns. In a pegmatite, which is a different rock type, which has got really big crystals, you can get things up to the centimeter size, and that's probably what people are fossicking about for. And I guess the other interesting thing about fossicking, the color of the zircon tells us about the amount of uranium. So if you're fossicking and you find a really dark one, it's got lots of uranium in it. The crystal structure is probably damaged. If you find one that's beautiful and crystalline, not as dark, it will have a lower uranium content. Um, so that's interesting. The next time you're fossicking, yeah, if you find yourself different zircon crystals, you'll be able to go, oh, well, that one's really cooked itself because it's so rich in uranium, and now that one hasn't cooked itself as much because it's got less uranium and less radiation damage.
Well, wow, I had no idea. I knew that they were very special for the reasons that were discussed, but that's cool that you can go out and actually look at it, and for people in Armidale, there is actually a little local area you can go and put
Yeah,
it to the test.
yeah.
Um, so other because I guess in my head, my brain was going, well, bigger means more information. Um, but it sounds like you're focusing a lot on the really small ones. So is it just from the uranium content? When they're larger, they've been around more and they're more likely to be radiation poisoned or radiation cooked?
Cooked.
Yeah.
So with the grains, it depends on the environment they're growing in. So zircon grows in a wide range of different environments. So it typically forms within a magma, so the rock is molten, and as that rock cools, the zircon grains crystallize, and the grains develop internal textures. So that means they develop like tree ring-like structures. So by having a beam-based technique and an analysis technique that allows us to shoot individual parts of the crystal, that's really powerful because it allows us to, analyze older bits of the crystal and then look at younger bits of the crystal as well. So zircon isn't just a recorder of the age of that magma. It can also be a recorder of later processes. So if we imagine we have a granite, so something like your conventional benchtop that you have in your kitchen, that forms, quite deep underground as a molten magma. That crystallizes zircon crystals. That's cool. Those crystals will have like this nice tree ring structure. But let's take that rock and bring it up to the surface because of erosion around it. But let's say it gets trapped within a mountain building event. So two continents collide, and that will create another event of heating and pressure. But our zircon is really interesting. It will probably record that event because it will grow a rind, it'll grow a rim of different composition on that crystal. So we now have the mechanism for that single crystal to tell us about two processes, the magma generation initially, but then a metamorphic event, so a changing event. Uh, so we can analyze both those different events and we can use the texture of the grain and the chemistry of the grain to actually understand what those processes are. And that's why, like, we can go deep, very
Yeah,
deep,
yeah,
and that's only
yeah.
part of the things we can do with these crystals. So they retain so much information that really allows to piece out this really detailed, this really nice narrative of the geological history of our planet.
And it's just, makes them so much cooler. And you can go out if you find one, you go, cool, this one has like a map of something. But I thank you so much, Chris, for coming in
No
and
worries.
speaking with me today.